Now on Nova. Take a thrill ride into a world stranger than science fiction, where you play the game by breaking some rules, where a new view of the universe pushes you beyond the limits of your wildest imagination. This is the world of string theory, a way of describing every force and all matter, from an atom to Earth to the end of the galaxies, from the birth of time to its final tick, in a single theory, a theory of everything. Our guide to this brave new world is Brian Greene, the best-selling author and physicist.
And no matter how many times I come here, I never seem to get used to it.
Can he help us solve the greatest puzzle of modern physics? That our understanding of the universe is based on two sets of laws that don't agree. Resolving that contradiction eluded even Einstein, who made it his final quest. After decades, we may finally be on the verge of a breakthrough. The solution is strings. Tiny bits of energy vibrating like the strings on a cello. A cosmic symphony at the heart of all reality. But it comes at a price. Parallel universes and 11 dimensions, most of which you've never seen.
We really may live in a universe with more dimensions than meet the eye.
People who've said that there are extra dimensions of space have been labelled crackpots or people who are bananas.
A mirage of science and mathematics? Or the ultimate theory of everything?
If string theory fails to provide a testable prediction, then nobody should believe it.
Is that a theory of physics or a philosophy?
One thing that is certain is that string theory is already showing us that the universe may be a lot stranger than any of us ever imagined.
Coming up tonight, it all started with an apple.
The triumph of Newton's equations come from the quest to understand the planets and the stars.
And we've come a long way since.
Einstein gave the world a new picture for what the force of gravity actually is.
Where he left off, string theorists now dare to go. But how close are they to fulfilling Einstein's dream? Watch The Elegant Universe right now.
Major funding for NOVA is provided by the Park Foundation.
Science. It's given us the framework to help make wireless communications clear. Sprint is proud to support NOVA.
We see an inventor. At Microsoft, your potential inspires us to create software that helps you reach it. Your potential, our passion.
Funding for The Elegant Universe is provided by the Alfred P. Sloan Foundation to enhance public understanding of science and technology. And by the National Science Foundation, America's investment in the future. Additional funding is provided by and by the George D. Smith Fund and the U.S. Department of Energy, fostering science and security. Major funding for NOVA is also provided by the Corporation for Public Broadcasting and viewers like you. Thank you.
50 years ago, this house was the scene of one of the greatest mysteries of modern science. A mystery so profound that today, thousands of scientists on the cutting edge of physics are still trying to solve it. Albert Einstein spent his last 2 decades in this modest home in Princeton, New Jersey. And in his second-floor study, Einstein relentlessly sought a single theory so powerful it would describe all the workings of the universe. Even as he neared the end of his life, Einstein kept a notepad close at hand, furiously trying to come up with the equations for what would come to be known as the theory of everything. Convinced he was on the verge of the most important discovery in the history of science, Einstein ran out of time, his dream unfulfilled. Now, almost a half-century later, Einstein's goal of unification, combining all the laws of the universe in one all-encompassing theory, has become the holy grail of modern physics. And we think we may at last achieve Einstein's dream with a new and radical set of ideas called string theory. But if this revolutionary theory is right, we are in for quite a shock. String theory says we may be living in a universe where reality meets science fiction. A universe of 11 dimensions, with parallel universes right next door. An elegant universe composed entirely of the music of strings. But for all its ambition, the basic idea of string theory is surprisingly simple. It says that everything in the universe, from the tiniest particle to the most distant star, is made from one kind of ingredient: unimaginably small, vibrating strands of energy called strings. Just as the strings of a cello can give rise to a rich variety of musical notes, the tiny strings in string theory vibrate in a multitude of different ways, making up all the constituents of nature. In other words, the universe is like a grand cosmic symphony, resonating with all the various notes these tiny, vibrating strands of energy can play. String theory is still in its infancy, but it's already revealing a radically new picture of the universe. One that is both strange and beautiful. But what makes us think we can understand all the complexity of the universe, let alone reduce it to a single theory of everything?
We have r mu nu minus a half g mu nu r, you remember how this goes, equals 8 pi g t mu nu. Comes from varying the Einstein-Hilbert action, we get the field equations, and this term, you remember what this is called? No, that's the scalar curvature. This is the Ricci tensor. Have you been studying this at all?
No matter how hard you try, you can't teach physics to a dog. Their brains just aren't wired to grasp it. But what about us? How do we know that we're wired to comprehend the deepest laws of the universe? Well, physicists today are confident that we are. And we're picking up where Einstein left off in his quest for unification.
Unification would be the formulation of a law that describes perhaps everything in the known universe from one single idea, one master equation. And we think that there might be this master equation because throughout the course of the last 200 years or so, our understanding of the universe has given us a variety of explanations that are all pointing towards one spot. They seem to all be converging on one nugget of an idea that we're still trying to find.
Unification is where it's at. Unification is what we're trying to accomplish. The whole aim of fundamental physics is to see more and more of the world's phenomena in terms of fewer and fewer and simpler principles.
We feel as physicists that if we can explain a wide number of phenomena in a very simple manner, that's somehow progress. There is almost an emotional aspect to the way in which the great theories in physics sort of encompass a wide variety of apparently different physical phenomena. So this idea that we should be aiming to unify our understanding is inherent, essentially, to the whole way in which this kind of science progresses.
And long before Einstein, the quest for unification began with the most famous accident in the history of science.
As the story goes, one day in 1665, a young man was sitting under a tree when all of a sudden he saw an apple fall from above. And with the fall of that apple, Isaac Newton revolutionized our picture of the universe.
In an audacious proposal for his time, Newton proclaimed that the force pulling apples to the ground and the force keeping the moon in orbit around the Earth were actually one and the same. In one fell swoop, Newton unified the heavens and the Earth in a single theory he called gravity.
The unification of the celestial with the terrestrial, that the same laws that govern the planets in their motions govern the tides and the falling of fruit here on Earth. It was a fantastic unification of our picture of nature.
Gravity was the first force to be understood scientifically, though 3 more would eventually follow. And although Newton discovered his law of gravity more than 300 years ago, his equations describing this force make such accurate predictions that we still make use of them today.
In fact, scientists needed nothing more than Newton's equations to plot the course of a rocket that landed men on the moon.
11, this is Houston.
Yet, there was a problem. While his laws described the strength of gravity with great accuracy, Newton was harboring an embarrassing secret. He had no idea how gravity actually works. For nearly 250 years, scientists were content to look the other way when confronted with this mystery. But in the early 1900s, an unknown clerk working in the Swiss patent office would change all that. While reviewing patent applications, Albert Einstein was also pondering the behavior of light. And little did Einstein know that his musings on light would lead him to solve Newton's mystery of what gravity is. At the age of 26, Einstein made a startling discovery: that the velocity of light is a kind of cosmic speed limit, a speed that nothing in the universe can exceed. But no sooner had the young Einstein published this idea than he found himself squaring off with the father of gravity. The trouble was, the idea that nothing can go faster than the speed of light flew in the face of Newton's picture of gravity. To understand this conflict, we have to run a few experiments. And to begin with,
let's create a cosmic catastrophe. Imagine that all of a sudden, and without any warning, the sun vaporizes and completely disappears.
Now, let's replay that catastrophe and see what effect it would have on the planets according to Newton. Newton's theory predicts that with the destruction of the sun, the planets would immediately fly out of their orbits, careening off into space.
In other words, Newton thought that gravity was a force that acts instantaneously across any distance, and so we would immediately feel the effect of the sun's destruction. But Einstein saw a big problem with Newton's theory.
A problem that arose from his work with light. Einstein knew light doesn't travel instantaneously. In fact, it takes 8 minutes for the sun's rays to travel the 93 million miles to the Earth. And since he had shown that nothing, not even gravity, can travel faster than light, how could the Earth be released from orbit before the darkness resulting from the sun's disappearance reached our eyes? To the young upstart from the Swiss patent office, anything outrunning light was impossible. And that meant the 250-year-old Newtonian picture of gravity was wrong.
If Newton is wrong, then why do the planets stay up? Because remember, the triumph of Newton's equations come from the quest to understand the planets and the stars. In particular, the problem of why do the planets have the orbits that they do. And with Newton's equations, you can calculate the way that the planets will move. Einstein's got to resolve this dilemma.
In his late 20s, Einstein had to come up with a new picture of the universe in which gravity does not exceed the cosmic speed limit. Still working his day job in the patent office, Einstein embarked on a solitary quest to solve this mystery. After nearly 10 years of racking his brain, he found the answer in a new kind of unification.
Einstein came to think of the three dimensions of space and the single dimension of time as bound together in a single fabric of space-time. It was his hope that by understanding the geometry of this four-dimensional fabric of space-time, that he could simply talk about things moving along surfaces in this space-time fabric.
Like the surface of a trampoline, this unified fabric is warped and stretched by heavy objects like planets and stars. And it's this warping or curving of space-time that creates what we feel as gravity.
A planet like the Earth is kept in orbit not because the sun reaches out and instantaneously grabs hold of it, as in Newton's theory, but simply because it follows curves in the spatial fabric caused by the sun's presence. So, with this new understanding of gravity, let's rerun the cosmic catastrophe. Let's see what happens now
if the sun disappears. The gravitational disturbance that results will form a wave that travels across the spatial fabric in much the same way that a pebble dropped into a pond makes ripples that travel across the surface of the water. So we wouldn't feel a change in our orbit around the sun until this wave reached the Earth. What's more, Einstein calculated that these ripples of gravity travel at exactly the speed of light.
And so, with this new approach, Einstein resolved the conflict with Newton over how fast gravity travels. And more than that, Einstein gave the world a new picture for what the force of gravity actually is. Its warps and curves in the fabric of space and time.
Einstein called this new picture of gravity general relativity. And within a few short years, Albert Einstein became a household name.
Einstein was like a rock star in his day. He was one of the most widely known and recognizable figures alive. He and perhaps Charlie Chaplin were the reigning kings of the popular media.
People followed his work, and they were anticipating because of this wonderful thing he had done with general relativity, this recasting the laws of gravity out of his head, there was the thought he could do it again, and people want to be in on that.
Despite all that he had achieved, Einstein wasn't satisfied.
He immediately set his sights on an even grander goal, the unification of his new picture of gravity with the only other force known at the time, electromagnetism.
Now, electromagnetism is a force that had itself been unified only a few decades earlier. In the mid-1800s, electricity and magnetism were sparking scientists' interest. These two forces seemed to share a curious relationship that inventors like Samuel Morse were taking advantage of in newfangled devices such as the telegraph. An electrical pulse sent through a telegraph wire to a magnet thousands of miles away produced the familiar dots and dashes of Morse code that allowed messages to be transmitted across the continent in a fraction of a second. Although the telegraph was a sensation, the fundamental science driving it remained something of a mystery. But to a Scottish scientist named James Clerk Maxwell, the relationship between electricity and magnetism was so obvious in nature that it demanded unification. If you've ever been on top of a mountain during a thunderstorm, you'll get the idea of how electricity and magnetism are closely related.
When a stream of electrically charged particles flows, like in a bolt of lightning, it creates a magnetic field, and you can see evidence of this
on a compass. Obsessed with this relationship, the Scot was determined to explain the connection between electricity and magnetism in the language of mathematics. Casting new light on the subject, Maxwell devised a set of 4 elegant mathematical equations that unified electricity and magnetism in a single force called electromagnetism. And like Isaac Newton before him, Maxwell's unification took science a step closer to cracking the code of the universe.
That was really the remarkable thing, that these different phenomena were really connected in this way. And it's another example of diverse phenomena coming from a single underlying building block or a single underlying principle.
Imagine that everything that you can think of which has to do with electricity and magnetism can all be written in 4 very simple equations. Isn't that incredible? Isn't that amazing? I call that elegant.
Einstein thought that this was one of the triumphant moments of all of physics and admired Maxwell hugely for what he had done.
About 50 years after Maxwell unified electricity and magnetism, Einstein was confident that if he could unify his new theory of gravity with Maxwell's electromagnetism, he'd be able to formulate a master equation that could describe everything, the entire universe.
Einstein clearly believes that the universe has an overall grand and beautiful pattern to the way that it works. And so to answer the question, why was he looking for the unification? I think the answer is simply that Einstein is one of those physicists who really wants to know the mind of God, which means the entire picture.
Today, this is the goal of string theory: to unify our understanding of everything, from the birth of the universe to the majestic swirl of galaxies, in just one set of principles, one master equation. Newton had unified the heavens and the earth in the theory of gravity. Maxwell had unified electricity and magnetism. Einstein reasoned all that remained to build a theory of everything, a single theory that could encompass all the laws of the universe, was to merge his new picture of gravity with electromagnetism.
He certainly had motivation. Probably one of them might have been aesthetics or this quest to simplify. Another one might have been just the physical fact that it seems like the speed of gravity is equal to the speed of light. So if they both go at the same speed, then maybe that's an indication of some underlying symmetry.
But as Einstein began trying to unite gravity and electromagnetism, he would find that the difference in strength between these two forces would outweigh their similarities. Let me show you what I mean.
We tend to think that gravity is a powerful force. After all, it's the force that right now is anchoring me to this ledge. But compared to electromagnetism, it's actually terribly feeble. In fact, there's a simple little test to show this. Imagine that I was to leap from this rather tall building. Actually, let's not just imagine it. Let's do it. You'll see what I mean.
Now, of course, I really should have been flattened, but the important question is, what kept me from crashing through the sidewalk and hurtling right down to the center of the earth?
Well, strange as it sounds, the answer is electromagnetism. Everything we can see, from you and me to the sidewalk, is made of tiny bits of matter called atoms. And the outer shell of every atom contains a negative electrical charge. So when my atoms collide with the atoms in the cement, these electrical charges repel each other with such strength that just a little piece of sidewalk can resist the entire Earth's gravity and stop me from falling. In fact, the electromagnetic force is billions and billions of times stronger than gravity.
That seems a little strange because gravity keeps our feet to the ground, it keeps the Earth going around the sun. But in actual fact, it manages to do that only because it acts on huge, enormous conglomerates of matter. You know, you, me, the Earth, the sun. But really at the level of individual atoms, gravity is a really incredibly feeble, tiny force.
It would be an uphill battle for Einstein to unify these two forces of wildly different strengths. And to make matters worse, barely had he begun before sweeping changes in the world of physics would leave him behind.
Einstein had achieved so much in the years up to about 1920 that he naturally expected that he could go on by playing the same theoretical games and go on achieving great things. And he couldn't. Nature revealed itself in other ways in the 1920s and 1930s, and the particular tricks and tools that Einstein had at his disposal that had been so fabulously successful just weren't applicable anymore.
You see, in the 1920s, a group of young scientists stole the spotlight from Einstein when they came up with an outlandish new way of thinking about physics. Their vision of the universe was so strange, it makes science fiction look tame, and it turned Einstein's quest for unification on its head.
Unification.
Led by Danish physicist Niels Bohr, these scientists were uncovering an entirely new realm of the universe. Atoms, long thought to be the smallest constituents of nature, were found to consist of even smaller particles, the now familiar nucleus of protons and neutrons, orbited by electrons. And the theories of Einstein and Maxwell were useless at explaining the bizarre way these tiny bits of matter interact with each other inside the atom.
There was a tremendous mystery about how to account for all this, how to account for what was happening to the nucleus as the atom began to be pried apart in different ways. And the old theories were totally inadequate to the task of explaining them. Gravity was irrelevant, it was far too weak, and electricity and magnetism was not sufficient.
Without a theory to explain this strange new world, these scientists were lost in an unfamiliar atomic territory, looking for any recognizable landmarks.
Then, in the late 1920s, all that changed. During those years, physicists developed a new theory called quantum mechanics, and it was able to describe the microscopic realm with great success. But here's the thing. Quantum mechanics was so radical a theory that it completely shattered all previous ways of looking at the universe.
Einstein's theories demand that the universe is orderly and predictable. But Niels Bohr disagreed. He and his colleagues proclaimed that at the scale of atoms and particles, the world is a game of chance. At the atomic or quantum level, uncertainty rules. The best you can do, according to quantum mechanics, is predict the chance or probability of one outcome or another. And this strange idea opened the door to an unsettling new picture of reality. It was so unsettling that if the bizarre features of quantum mechanics were noticeable in our everyday world, like they are here in the Quantum Cafe, you might think you'd lost your mind.
The laws in the quantum world are very different from the laws that we are used to. Our daily experiences are totally different from anything that you would see in the quantum world. The quantum world is crazy. It's probably the best way to put it. It's a crazy world.
For nearly 80 years, quantum mechanics has successfully claimed that the strange and bizarre are typical of how our universe actually behaves on extremely small scales.
At the scale of everyday life, we don't directly experience the weirdness of quantum mechanics.
But here, in the Quantum Cafe, big, everyday things sometimes behave as if they were microscopically tiny. And no matter how many times I come here, I never seem to get used to it.
I'll have an orange juice, please.
I'll try.
I'll try, she says.
You see, they're not used to people placing definite orders here in the Quantum Cafe because here, everything is ruled by chance. While I'd like an orange juice, there's only a particular probability that I'll actually get one. And there's no reason to be disappointed with one particular outcome or another because quantum mechanics suggests that each of the possibilities, like getting a yellow juice or a red juice, may actually happen. They just happen to happen in universes that are parallel to ours, universes that seem as real to their inhabitants as our universe seems to us.
If there are 1,000 possibilities and quantum mechanics cannot with certainty say which of the 1,000 it will be, then all 1,000 will happen. Yeah, you can laugh at it and say, well, that has to be wrong. But there are so many other things in physics which at the time that people came up with had to be wrong, but it wasn't. You have to be a little careful, I think, before you say this is clearly wrong.
And even in our own universe, quantum mechanics says there's a chance that things we'd ordinarily think of as impossible can actually happen. For example, there's a chance that particles can pass right through walls or barriers that seem impenetrable to you or me.
There's even a chance that I could pass through something solid, like a wall. Now, quantum calculations do show that the probability for this to happen in the everyday world is so small that I'd need to continue walking into the wall for nearly an eternity before having a reasonable chance of succeeding. But here, these kind of things happen all the time.
You have to learn to abandon those assumptions that you have about the world in order to understand quantum mechanics. In my gut, in my belly, do I feel like I have a deep intuitive understanding of quantum mechanics? No.
And neither did Einstein. He never lost faith that the universe behaves in a certain and predictable way. The idea that all we can do is calculate the odds that things will turn out one way or another was something Einstein deeply resisted.
Quantum mechanics says that you can't know for certain the outcome of any experiment. You can only assign a certain probability to the outcome of any experiment. And this Einstein disliked intensely. He used to say, God does not throw dice.
Yet experiment after experiment showed Einstein was wrong, and that quantum mechanics really does describe how the world works at the subatomic level.
So quantum mechanics is not a luxury, something that you can do without. I mean, why is water the way it is? Why does light go straight through water? Why is it transparent? Why are other things not transparent? How do molecules form? Why are they reacting the way they react? The moment that you want to understand anything at an atomic level, as non-intuitive as it is, at that moment you can only make progress with quantum mechanics.
Quantum mechanics is fantastically accurate. There has never been a prediction of quantum mechanics that has contradicted an observation. Never.
By the 1930s, Einstein's quest for unification was floundering, while quantum mechanics was unlocking the secrets of the atom. Scientists found that gravity and electromagnetism are not the only forces ruling the universe. Probing the structure of the atom, they discovered two more forces. One, dubbed the strong nuclear force, acts like a superglue, holding the nucleus of every atom together, binding protons to neutrons. And the other, called the weak nuclear force, allows neutrons to turn into protons, giving off radiation in the process. At the quantum level, the force we're most familiar with, gravity, was completely overshadowed by electromagnetism and these two new forces.
Now, the strong and weak forces may seem obscure, but in one sense at least, we're all very much aware of their power. At 5:29 on the morning of July 16th, 1945, that power was revealed by an act that would change the course of history. In the middle of the desert in New Mexico, at the top of a steel tower, about 100 feet above the top of this monument, the first atomic bomb was detonated.
It was only about 5 feet across, but that bomb packed a punch equivalent to about 20,000 tons of TNT. With that powerful explosion, scientists unleashed the strong nuclear force, the force that keeps neutrons and protons tightly glued together inside the nucleus of an atom. By breaking the bonds of that glue and splitting the atom apart, vast, truly unbelievable amounts of destructive energy were released.
We can still detect remnants of that explosion through the other nuclear force, the weak nuclear force, because it's responsible for radioactivity. And today, more than 50 years later, the radiation levels around here are still about 10 times higher than normal. So, although in comparison to electromagnetism and gravity, the nuclear forces act over very small scales, their impact on everyday life is every bit as profound.
But what about gravity? Einstein's general relativity. Where does that fit in at the quantum level?
Quantum mechanics tells us how all of nature's forces work in the microscopic realm, except for the force of gravity. Absolutely no one could figure out how gravity operates when you get down to the size of atoms and subatomic particles. That is, no one could figure out how to put general relativity and quantum mechanics together into one package.
For decades, every attempt to describe the force of gravity in the same language as the other forces, the language of quantum mechanics, has met with disaster.
You try to put those two pieces of mathematics together, they do not coexist peacefully.
You get answers that the probabilities of the event you're looking at are infinite. Nonsense. It's not profound, it's just nonsense.
It's very ironic because it was the first force to actually be understood in some decent quantitative way, but it still remains split off and very different from the other ones.
The laws of nature are supposed to apply everywhere. So if Einstein's laws are supposed to apply everywhere, and the laws of quantum mechanics are supposed to apply everywhere, well, you can't have two separate everywheres.
In 1933, after fleeing Nazi Germany, Einstein settled in Princeton, New Jersey. Working in solitude, he stubbornly continued the quest he had begun more than a decade earlier to unite gravity and electromagnetism. Every few years, headlines appeared proclaiming Einstein was on the verge of success, but most of his colleagues believed his quest was misguided and that his best days were already behind him.
Einstein in his later years got rather detached from the work of physics in general and stopped reading people's papers. I didn't even think he knew there was such a thing as the weak nuclear force. He didn't pay attention to those things. He kept working on the same problem that he had started working on as a younger man.
When the community of theoretical physicists begin to probe the atom, Einstein very definitely gets left out of the picture. He, in some sense, chooses not to look at the physics coming from these experiments. That means that the laws of quantum mechanics play no role in his sort of further investigations. He's thought to be this doddering, sympathetic old figure who led an earlier revolution but somehow fell out of it.
It is as if a general who was a master of horse cavalry, who has achieved great things as a commander at the beginning of the First World War, would try to bring mounted cavalry into play against the barbed wire trenches and machine guns of the other side.
Albert Einstein died on April 18th, 1955. And for many years, it seemed that Einstein's dream of unifying the forces in a single theory died with him.
So the quest for unification becomes a backwater of physics. By the time of Einstein's death in the 50s, almost no serious physicists are engaged in this quest for unification.
In the years since, physics split into two separate camps. One that uses general relativity to study big and heavy objects, things like stars, galaxies, and the universe as a whole. And another that uses quantum mechanics to study the tiniest of objects like atoms and particles. This has kind of been like having two families that just cannot get along and never talk to each other, living under the same roof. There just seemed to be no way to combine quantum mechanics
and general relativity in a single theory that could describe the universe on all scales.
Now, in spite of this, we've made tremendous progress in understanding the universe. But there's a catch. There are strange realms of the cosmos that will never be fully understood until we find a unified theory. And nowhere is this more evident than in the depths of a black hole. A German astronomer named Karl Schwarzschild first proposed what we now call black holes in 1916. While stationed on the front lines in World War I, he solved the equations of Einstein's general relativity in a new and puzzling way. Between calculations of artillery trajectories, Schwarzschild figured out that an enormous amount of mass, like that of a very dense star, concentrated in a small area, would warp the fabric of space-time so severely that nothing, not even light, could escape its gravitational pull. For decades, physicists were skeptical that Schwarzschild's calculations were anything more than theory. But today, satellite telescopes probing deep into space are discovering regions with enormous gravitational pull that most scientists believe are black holes. Schwarzschild's theory now seems to be reality. So, here's the question. If you're trying to figure out what happens in the depths of a black hole, where an entire star is crushed to a tiny speck, do you use general relativity because the star is incredibly heavy, or quantum mechanics because it's incredibly tiny? Well, that's the problem. Since the center of a black hole is both tiny and heavy, you can't avoid using both theories at the same time. And when we try to put the two theories together in the realm of black holes,
they conflict, it breaks down, they give nonsensical predictions, and the universe is not nonsensical, it's got to make sense.
Quantum mechanics works really well for small things, and general relativity works really well for stars and galaxies. But the atoms, the small things, and the galaxies, they're part of the same universe. So there has to be some description that applies to everything. So we can't have one description for atoms and one for stars.
Now, with string theory, we think we may have found a way to unite our theory of the large and our theory of the small and make sense of the universe at all scales and all places. Instead of a multitude of tiny particles, string theory proclaims that everything in the universe, all forces and all matter, is made of one single ingredient, tiny, vibrating strands of energy known as strings.
A string can wiggle in many different ways, whereas of course a point can't. And the different ways in which the string wiggles represent the different kinds of elementary particles.
It's like a violin string, and it can vibrate just like violin strings can vibrate. Each note, if you like, describes a different particle.
So it has incredible unification power. It unifies our understanding of all these different kinds of particles.
So unity of the different forces and particles is achieved because they all come from different kinds of vibrations of the same basic string.
It's a simple idea with far-reaching consequences.
What string theory does is it holds out the promise that, look, we can really understand questions that you might not even have thought were scientific questions. Questions about how the universe began, why the universe is the way it is at the most fundamental level. The idea that a scientific theory that we already have in our hands could answer the most basic questions is extremely seductive.
But this seductive new theory is also controversial. Strings, if they exist, are so small there's little hope of ever seeing one.
String theory and string theorists do have a real problem. How do you actually test string theory? If you can't test it in the way that we test normal theories, it's not science, it's philosophy. And that's a real problem.
If string theory fails to provide a testable prediction, then nobody should believe it. On the other hand, there's a kind of elegance to these things. And given the history of how theoretical physics has evolved thus far, it is totally conceivable that some, if not all, of these ideas will turn out to be correct.
I think 100 years from now, this particular period when most of the brightest young theoretical physicists worked on string theory will be remembered as a heroic age when theorists tried and succeeded to develop a unified theory of all the phenomena of nature. On the other hand, it may be remembered as a tragic failure. My guess is that it'll be something like the former rather than the latter. But ask me 100 years from now, then I can tell you.
Our understanding of the universe has come an enormously long way during the last 3 centuries. Just consider this. Isaac Newton, who's perhaps the greatest scientist of all time, once said, "I have been like a boy, playing on the seashore, diverting myself in now and then finding a smoother pebble or prettier shell than usual, while the great ocean of truth lay before me, all undiscovered." And yet, 250 years later, Albert Einstein, who was Newton's true successor, was able to seriously suggest that this vast ocean, all the laws of nature, might be reduced to a few fundamental ideas expressed by a handful of mathematical symbols.
And today, a half-century after Einstein's death, we may at last be on the verge of fulfilling his dream of unification with string theory. But where did this daring and strange new theory come from? How does string theory achieve the ultimate unification of the laws of the large and the laws of the small? And how will we know if it's right or wrong?
No experiment can ever check up what's going on at the distances that are being studied. The theory is permanently safe. Is that a theory of physics or a philosophy?
It isn't written in the stars that we're going to succeed, but in the end, we hope we will have a single theory that governs everything.
On NOVA's website, go behind the scenes with Brian Greene. Journey into the subatomic world. Play with strings. Picture other dimensions and much more. Find it on pbs.org. To order this program on VHS or DVD, or the book The Elegant Universe, please call WGBH Boston Video at 1-800-255-9424.
Next time on Nova, play hard, break some rules, and push the limits of your wildest imagination. Brian Greene takes you on a quest for the theory of everything. PBS presents Nova, The Elegant Universe.
Nova is a production of WGBH Boston. Major funding for Nova is provided by the Park Foundation.
We see Teacher of the Year. We see kids reaching their potential. It's what inspires us to create software that helps you reach yours.
Science. It's given us the framework to help make wireless communications clear. Sprint is proud to support NOVA.
Funding for the Elegant Universe is provided by the Alfred P. Sloan Foundation to enhance public understanding of science and technology. And by the National Science Foundation, America's investment in the future. Additional funding is provided by and by the George D. Smith Fund and the U.S. Department of Energy, fostering science and security. Major funding for NOVA is also provided by the Corporation for Public Broadcasting and viewers like you. Thank you.
We are